In this video, we are going to discuss the ground state of helium atom. Actually, we are not going to discuss this in detail. We'll just go through the surface. This could have been included in the last video itself, but I didn't want to make that one lengthy. So, coming into helium atom, we know it's a system of two electrons, right? So, as electrons are fermions, we know their wave functions are supposed to be anti-symmetric. So, when we consider a quantum mechanical system, the total wave function of the system is the product of space wave function and the spin wave function, right? We have to consider the space part as well as the spin part, and a product of these two will give us the total wave function. As we know, electrons are having spin half. So, a system of two electrons is supposed to have a spin of 1 or 0, right? So, according to this, we have already discussed these wave functions in detail in the third module while we discussed the system of two fermions. We have discussed in detail about the triplet state as well as singlet state. Okay, so as the electrons are having spin half, the spin of the two electron system, that is the spin of helium atom, could be either 1 or 0, and corresponding to this we have three states. For spin 1 we have 3 states. Okay, corresponding to spin 1 we have 3 states, and corresponding to spin 0 we have 1 state. I'll just mention it. When spin is equal to 1, we will have the m value minus 1, 0, 1, right? So, we will have, if we are representing the state in terms of s and m, we will have corresponding to s equal to 1, the states 1 minus 1, 1 0 and 1 1. Okay, these are the triplet state. S equal to 1 states are the triplet state, and corresponding to s equal to 0 we have m equal to 0, and we have the singlet state 0 0, right? This is just the SM representation. So, we have this triplet state represented by get plus plus, for which s value is 1 and m value is 1. Then 1 by root 2 into plus minus plus minus plus for s value 1, m value 0, and for s equal to 1, m equal to minus 1, we have get minus minus, right? So, these are the triplet states. So, we prefer to denote them like this. Okay, these 3 indicates the they belong to the triplet. Okay, so we represent these states by their m value, and we will just put a 3 here to represent they are from the triplet. Okay, so this first state with m equal to 1 is represented as chi 1 3, and this one is represented as chi 0 3, and this one is represented as chi minus 1 3. Okay, and for singlet state we have 1 by root 2 plus minus 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 plus. Since it is singlet, we represent it by 1. Okay, so it is chi 1 0. So here I have written these notations based on s and m values. Okay, this upper left number indicates s value, and this is m value. So you better represent these states as this. Okay, for triplet use 3 and for singlet use 1. Anyway, when we look into these states, we can see this is symmetric, right? This is also symmetric, and this is also symmetric. That means all the triplet states are symmetric, while the singlet state is antisymmetric, right? That is, if we exchange the particles, there is no change in wave functions corresponding to these states. But here for the singlet state, we will have a negative value, right? So all the triplet states are symmetric, while the singlet state is antisymmetric. So we have already said this is about the spin part, right? This is the spin wave functions of the system. This is the wave functions corresponding to the spin part. Okay, so we have already said that the total wave function of the system, our helium atom, must be antisymmetric, right? So for the total wave function to be antisymmetric, okay, we know if we are representing total wave function like this psi s is equal to psi space part wave function into psi spin, right? And we need this total wave function to be antisymmetric. For this to be antisymmetric, the possible combinations are, if this is antisymmetric, that space part is antisymmetric, this has to be symmetric, right? And if this is symmetric, this has to be antisymmetric. Then only the product will be antisymmetric, right? So these are the possibilities. Symmetric and antisymmetric are not possible, because symmetric will result in total wave function to be symmetric, right? And antisymmetric will give rise to a symmetric wave function. Total wave function will be symmetric. So the only possibilities are these two, right? So with that, we have already said that, okay, we have already said that for the spin part, we have 4 states, right? 4 states, and all the triplet states are symmetric. All the triplet states are symmetric. So the possible combinations of total wave function for the helium atom could be psi s, that is space part symmetric, okay, psi s. Then if this one is symmetric, that space part is symmetric, we must have the spin part antisymmetric, right? Spin part antisymmetric is the singlet state, okay. So this is the one possible wave function. Then if the space part is antisymmetric, we can have these 3 combinations. Right, that is, for the triplet states, as they are symmetric, we'll have to take the space part antisymmetric. And for the singlet state, as it is antisymmetric, we have to take the space part symmetric, okay. So these 4 are the possible wave functions, okay. Here I have written these symmetric and antisymmetric wave functions, which we have already mentioned earlier, okay. Now when we look into Hamiltonian of this system, if we write the operator corresponding to the Hamiltonian, we will have minus h cross square by 2 mu del 1 square plus del 2 square, okay. This is corresponding to the kinetic energy of the 2 electrons, okay. And we have minus 2 e square by 1 by r1 plus 1 by r2, which is the potential energy operator. Then in addition to that, we will have a term e square by r12. From where did this term arises? This is due to the repulsion between the 2 electrons, okay. E square by r12, where here this r1 and r2 are the radial distance of the 2 electrons from the center of atom, and this r12 is the separation between the two electrons. Okay, so the Hamiltonian of the system is given by this, where this term is from the repulsion between two electrons. So we usually write this Hamiltonian as this part, this kinetic energy plus potential energy part, we will write it as H0. We represent it as H0, and this part we represent as H1. So our H is H0 plus H1. Okay. Where this H1 is due to that mutual repulsion. So when we calculate the contribution of H1, this H1 Hamilton, this is actually perturbation, which you will deal with this in third semester. So when we calculate the contribution of H1 to the energy of the system, we make use of first order perturbation theory. We are not going into details. We'll just conclude the results. Okay. So when we calculate the contribution of H1 to the energy of the system using first order perturbation theory, we can see the contribution of H1 for the triplet state is less than that for the singlet state. Okay, the contribution of H1 to the total energy of the system is lesser for the triplet states. Okay, that is, the singlet states is always having higher energy than the triplet state. Okay, now when we look into the ground state of the helium atom, the ground state of the helium atom, for that we have both the states equal to oneness. That means the two electrons are occupied in the K shell itself. Okay, for the ground state of helium atom, the two electrons are occupied in the oneness subshell of K shell. Okay, K shell only have that oneness subshell, right? So if the two electrons are occupied in the K shell, we have n equal to 1, L equal to 0. That means for this we will have the anti-symmetric wave function 0, because the two electrons are occupying the same state, right? Two electrons are occupying the same state means this is our anti-symmetric wave function. Okay, we have a minus sign in between. So when the two electrons are occupied in the same state, the wave function vanishes. So for the ground state of helium atom, we have the anti-symmetric wave function vanishing. So as a result, we can see out of the 4 combinations possible, these are the 4 combinations possible, right? For the ground state, we have psi A equal to 0. That means this and this does not represent the ground state. So the ground state wave function of the helium atom turns to be psi s chi 01, that singlet state combination, right? So the only allowed wave function will be psi s chi 01. Okay, so it is because of that symmetry character we were able to get this wave function. So this symmetric character of the wave function arising from identity of the electrons provided us to understand the features of this helium atom, such as ground state and the energy differences and all those things. Okay, so that's the importance of symmetry character of the wave functions arising from the identity of electrons. Okay, so with this we have completed our 5th module.